rates of change are one of the big things that inspired the study and the invention of calculus in general. So it's natural that we would use what we know already to start to look at rates of change. Now, if you go back to studies that you've had in math before, you know that when we talk about rates, what we do is we take 2 points, we say, all right, what's the value at the start, what's the value at the end, how long of a time has passed, and that gets you your average rate of change. Think again like your average miles per hour. If I know that I traveled 300 miles and I did it in 6 hours, then my average speed was 50 miles per hour. So if we have some sort of quantity function, Q, then Q at the end point minus Q at the starting point divided by the total change in time. It doesn't actually have to be time, but for practical purposes it's time. This is going to be our average change, so our average rate of change. So for example, if we have a ball and it's dropped from a height of 100 feet, then its position, S of t, can be modeled by this function. So what that tells me is that at the 0, the time that it's dropped, so basically the event has begun, but it hasn't actually started falling, it's still just touching your hand. You plug in 0, you're at 100 feet. But at some point t equals, I don't know, right around 3, 2.5, this thing's going to hit the ground. And we might want to find the average rate of change from 1 second after it falls to 2 seconds. So, what's that rate of change over that time? What's the average speed that it's going in just that in that 1 second interval? So we can find that by finding the change in position divided by the change in time. So we plug in S at 2, we subtract S at 1, and then we subtract the difference in their time steps. So 36 minus 84. So you plug in 2 here, you'll get 36. You plug in 1, you'll get 84. And you get negative 48 feet. Now you get negative 48 feet. And that makes sense because you're falling downward, right? If you were going up, you'd have a positive velocity. If you were going down, you'd have a negative velocity. So your rate of change here is negative 48 feet. Which is good, great, grand, and wonderful. You've done this before, likely, with previous math courses. But we want to use calculus here. So what calculus can do for us is instead of approximating the velocity at time equals 1, we could find, I could take t equals 2, or I could take from 1 to 1/2, or 1 to 1.1, or 1 to 1.0001, and I could get that time step fine enough that I could approximate the speed at t equals 1. But why do that when we have calculus to give us the instantaneous rate of change? So if I set up this parameterized function where I have some change in time, and I start making that change infinitesimally small, just pinching it closer and closer, what I do is I end up with a derivative. And what we find is that the velocity is the derivative of position. So if you have a position function and you want to find the velocity, you just take a derivative. You don't have to overthink it. You simply say, oh, I'm going around, derivative, boom, I have it. Now it's important to note that velocity, because it's just a function, it could be positive, it could be 0, it could be negative. Notice here that this is an average, but the average velocity was negative. But when we talk about speed is the absolute value of velocity. That means it's non-negative. Non-negative means it could be 0 or positive. And that makes sense. Like, again, when you're driving, if you're driving north of where you are, you're not going to say, oh, I was going positive 20 miles per hour or positive 30 miles per hour. And if you're traveling south, you're not going to say I went negative 30 miles. No, you're going to describe speed in terms of a magnitude. You're going to describe it as a positive value or 0. So that's just the that's why that makes sense. It's the absolute value of the velocity. So for this example, if I wanted to find the velocity, which is s prime, I simply take the derivative here by the power rule. The 2 comes down, and we subtract 1 from the power, and then by the constant multiple rule, we multiply it by that negative 16. So 2 times negative 16 is negative 32 t. So if we wanted to find the velocity at 1, it'd just be negative 32 feet per second. This is actually feet per second. I don't know why I wrote feet. That's feet per second. Right? Because this is a change in seconds, and this is a change in feet. So this is negative 32 feet per second at s equals 1. Now at s equals 2, it's negative 64 feet per second. So it's picking up speed. But it's traveling even more quickly as it goes down. And what we find is that s at 1.5 turns out to be the average here. That's actually kind of surprising. It's usually not in the middle for a function like this, but hey, what can you do? So realistically, that's how you apply functions to get velocities given a position function.